Okay. So the article that none of you have read, sadly, it was basically proposing an alternative to dark matter to explain our observations. So oh, sorry. Okay. So initially, why we need dark matter or something like it. In the 1930s, it was observed that the outer edges of galaxies were rotating a lot faster than we expected them to be, and the matter we were observing was not enough to support this. So, two theories that could explain this discrepancy: lambda-cold dark matter, which is probably what you're more familiar with. It has yet to be observed, but it does, and it constitutes dark matter and dark energy are 95% of the galaxy, and they do solve this issue of galaxies having higher rotational velocities at their edges, but we haven't observed anything like it. So that was kind of the motivation for the authors of this paper to pursue modified Newtonian dynamics, which actually changes the laws of gravity, which is a bit of a bold approach, but they have their reasons. So basically, it adds a brand new parameter to Newton's laws of gravity, and it's had some success, actually. Some things we've observed, such as the Tully-Fisher relation, which basically says that a galaxy's intrinsic luminosity is proportional to its rotational velocity. That can be reproduced with this model. So it has, it works in some cases. And it could be justified if matter was polarized, which is an interesting idea. So as of now, it's not justified, but if we could show that matter was polarized with matter and antimatter, it would have a reason to exist. So antimatter would, this is a little weird, it would produce a negative active gravitational mass. So its inertial mass is like its mass, like what you would put in F equals ma, but negative active gravitational mass would be what the gravitational force it exerts upon other things. So if that was negative, it would exert a negative gravitational force on other things. Did I explain that right?
I have no idea.
Okay, I think so.
Keep going and we'll circle.
Yeah, that's what I read.
This is fast.
So yeah, it was definitely it's a bit out there compared to dark matter, but they just really didn't like that most of the universe has yet to be observed. So this doesn't add any new particles, it just changes the math a lot. And here, that's the V of r is the velocity as a function of radius, and then that's just the radius of the galaxy. So Newton's model obviously falls off, which was the issue we were having, and the Dirac-Milne universe model succeeds. It matches what we've been observing. Yeah. So the polarization of matter is consistent with modified Newtonian dynamics, which has yet to be proven. So if it was, we would be able to justify using this model. Again, it was just their dissatisfaction with nobody being able to observe dark matter or dark energy. Yeah. So they wanted to try something different. So there's one discrepancy in modified Newtonian dynamics. The parameter they add is constant. It's like a fundamental constant of the universe. But the authors of this article, the Dirac-Milne cosmology, they showed it was affected by redshift. So that is something to be resolved. Why are the two different papers?
Will that number be changing over time?
Yeah, saying different things. And also the Dirac-Milne model, it's been shown to be consistent with things such as distance and age and other factors of the universe. And this paper adds rotational velocity to the list of things it could support effectively. And the original paper was Monlight behavior in the Dirac-Milne universe. And the second one was just one I looked at to explain Dirac-Milne universes. So that was my article. You have a question?
Yeah, maybe.
Okay.
So So this kind of seems like it's combining what the problems that we deal with that we try to explain with dark matter. It also seems to be combining that a little bit with matter antimatter asymmetry.
Yeah, they mattered. In a Dirac-Milne universe, they mentioned that it's a matter antimatter symmetric universe.
Right. Okay. So then it would just imply that. So then their solution to this asymmetry would be that our perceived asymmetry is just a local phenomenon.
That actually, I do not know for sure.
Yeah, right. Where is all that in?
Yeah, that is also an issue. Like, we obviously have not seen equal numbers. So, but that is a requirement for this to work.
Interesting.
Yes. Dan?
Did they mention at all why, so if dark matter is a phenomenon that's actually created by antimatter, then why haven't we been able to detect?
It wasn't so much that dark matter is created by antimatter. It was just this model answers the same question dark matter does,
Right,
just in a different way.
We haven't been able to detect anything causing this phenomenon. Did they explain why we haven't been detecting any antimatter then?
Oh, they did not.
So, I've met so many questions, and I'm sure you don't have the answers, but let's ask them anyway.
Okay.
So go back. There was a phrase in there that caught my attention. Keep going. I think it was one before this.
That was,
Oh, that was it.
yes.
It was the one where negative gravitation.
Oh, yeah, that was this one.
So how does that work? So matter and antimatter, matter particles attract.
Yeah.
Antimatter particles presumably attract. Do matter particles then repel?
I think that would be the implication. Like, it would produce a negative gravitational force.
It's the opposite of the charge phenomenon. Opposites repel and like charges attract.
Yeah, because matter and antimatter annihilate when they. It was very. They were like very much modifying physics, as we know.
I'm fine with all of this. This seems great to me.
If that were true, though, then that would reconcile really nicely with the fact that like any area where there was a homogeneous mixture,
right,
would have nothing.
That's true. That's true. Although any mixture obviously is going to be catastrophic, right? Because if matter particles interact, then they annihilate.
And I mean, how like
they are.
If there's an equal mixture, we can expect when you zoom out far enough there to be homogeneity. But then,
right,
like,
locally you have either antimatter galaxies or matter galaxies.
Right. So maybe we're just maybe the observable universe is on that skip is too small to notice the homogeneity.
I have a question.
Yeah.
Who made this paper? Is it just like some?
It was.
some dude?
Yeah, just some guy in a basement. It was me, actually. My first original work. It was these people in the first thing.
Just direct sentence of Newton that are angry that everything.
I'll say this is not a crazy thing to be doing. I mean, dark matter is really problematic, right? We don't know where 95% of the energy in the universe is, and 85% of the matter in the universe, or more, right? That's a big problem in 2021 to not understand not know what most of the matter in the universe is. If you can explain this phenomenon without having to resort to some invisible matter that we can't see, that's a much cleaner solution to the problem. And if you can, there's a Nobel Prize for him on it, just waiting for you.
Maybe they're on their way to get it.
Probably starting the engraving process already to figure this out. It's that important. And people have tried really hard to modify gravity to try to explain all these observations without needing dark matter. But so far, none of them have really done a reasonable job, even close to reasonable job. And there's other reasons to believe that there's matter out there that we're not seeing.
The use of the word antimatter.
Yeah.
It seems to be different from the term, from how we use it in nuclear physics at all. Because, I mean, if we were to just use the nuclear antimatter, like what we produce in a lab, that, neutrons are going to exist in either anti-helium or antihelium, right? Like
No, I
if
think
we're
there's
just switching-
anti-neutrons too.
we have anti-neutrons.
I think there's, because you're made out of anti-quarks, and anti-quarks are different than quarks.
It's
not-
it is more than.
I think
just-
it's more than just charge flip. It's
Okay.
the anti of those particles.
Okay.
That's my understanding anyway. I'm no nuclear physicist.
Neither am I, clearly.
Get that repetitive.
Yeah, we'll bring him in.
Yeah, questions.
Yeah. So for those who don't know, what antimatter, matter symmetry, maybe some of you don't know these terms. Early in the universe, when there was high energy and really high temperatures, like seconds or fractions of seconds after the Big Bang, and it's so hot, antimatter, matter particles are running around pretty much at will, annihilating each other. When an antimatter particle and a particle collide, then they annihilate one another and they emit energy. And there was some time in the first second or so that the universe cooled enough that there wasn't enough energy to spontaneously make these particles again after they annihilate each other. And at that point, it should have been that there were equal numbers of matter and antimatter particles in the universe, and all of the matter in the universe went away. It happened to be that for every million particles of antimatter, there were probably like 1,000,001 particle of matter, and that's what we think is now all the matter in the universe that we see today. And so they pretty much all annihilate each other, but there's a tiny little bit left over of matter particles, and that's where we're at now.
Is the only reason matter is matter and antimatter is antimatter is because matter is the one that survived?
Yeah.
Like if
That's right.
antimatter had if there'd been
That's
more
right.
of that, we'd be calling antimatter matter?
That's right. I think
So
the
weird.
universe would look about the same. It would work the same. Everything, all the properties would be the same. We just,
I like to think there's just a negative sign in front of that.
there's a negative sign. That's right. although we probably defined it so that was a positive anyway.
Yeah.
It wouldn't matter.
On the question of detection, wouldn't like anti-hydrogen produce the same spectral lines?
Yes, and that's been confirmed. We have been able to make anti-hydrogen in the lab with anti-protons and anti-electrons, and we have measured its spectrum, and you get the same line, the same energy patterns, the same quantum mechanics works the same on antiparticles.
How did they contain it long enough to
I don't know.
measure that?
I
Okay.
don't know.
But
But I-
the next star system isn't.
That's a great question. We don't.
So then,
Wow.
then
So we
don't.
could land a spaceship and just
I-
disintegrate.
It's possible, but
on what basis are we declaring asymmetry?
Lasted 2 hours.
because the way stars are formed in the galaxy, they're not formed independently. Right? All of the galaxy is kind of homogenized at some level
Right,
and has
sure.
interacted with other stuff in the galaxy. And if there were antimatter stars out there,
They'd be constantly injecting anti.
yeah, and where would it have formed from, and where are the antimatter clouds of gas out there that form these anti-stars? And it's hard to imagine this happening within the galaxy, or even within a galaxy cluster, right? You'd have to get into the larger scale universe before you can have stuff that's separated enough to be able to have that even happen. But as far as we know, antimatter behaves exactly the same as matter. In fact, I watched a Minute Physics video about this last week. How would we know if aliens communicated with us are antimatter or matter people? And there's a couple of, I guess, reactions that are not symmetric. But there are very specific weird decays of certain pion, kaon things where the antimatter and matter particles aren't mirror imaged, and there's actually right-handed and left-handed asymmetry there between those two. But it's really hard to do, and it takes some really so it isn't completely symmetric, but it's in almost every way it's symmetric.
If they were able to produce anti-hydrogen in a lab, would they have observed a negative gravitational effect if it existed?
Yeah, probably not. Because remember, the gravitational effect is so much weaker than the electrical effect or any other forces out there. You probably need to start building macroscopic things out of antimatter particles to be able to measure them.
Like that antimatter baseball.
Get pumped out.
An antimatter Cavendish experiment.
Yeah. Yeah.
Part of the whole dark matter problem is we know that galaxies have to be full of dark matter, right? So if we have a universe where dark matter and matter repel, then why would the dark matter galaxies be in the same spots as the matter galaxies? Wouldn't they be completely separate because they're constantly pushing?
Oh, you're talking about antimatter galaxies? The dark, in this model, you don't need dark matter.
Right, sorry, dark matter is antimatter. But I'm just saying,
Well, it's not even that. It's that gravity
It's
works
like
different.
yeah, it's like a different.
It's not. You
theory.
don't need antimatter in the Milky Way to explain the rotation curves. You can do it with the different way in which gravity works based on matter and antimatter behaving in this weird way. I think that was what I interpreted. And then you don't need dark matter at all, or antimatter in the Milky Way.
Okay, so if there's no antimatter in the Milky Way, then how would if gravity is behaving differently because of antimatter, but there's no antimatter in the Milky Way, how would that make gravity different in the Milky Way?
I don't know.
that's what I'm saying.
This is the Mond theory, though, modified Newtonian dynamics. So usually what happens is, what's Newtonian dynamics? You can. It's the force of gravity is Gm1 m2 over d squared, right? What if there's what if this d squared term, so what does that look like, right? It looks like this, right? It just goes to 0. But what if there's it's plus some really small constant, right? And then no matter how far you get out, there's still some force there. I think, I don't remember exactly how modified Newtonian dynamics works, but it's something like this, where this is a really small number, really hard to measure, like really small. But on the scale of galaxies, it becomes important and can help to explain why you get all this force seemingly from nowhere out of the edges of these galaxies.
So you never have escape velocity then if you have that.
I think you can still get escape velocities, especially if this is so small. I don't know. Again, this may not even be what the right thing is, but it's something like this.
Could this be transferred into like an Einsteinian?
Good question. Good question. This is pure Newtonian. How does this work with general relativity? I have not the foggiest idea.
I mean, so like when we're doing when we're like modeling an experiment, I can just, usually whenever I add a parameter, I have to justify it, right?
Yeah.
So, but like, it sounds like, do they have a physical explanation behind this added
Yeah,
parameter?
that's
Or
a
is
good
it just
question.
The math works out when I add this parameter, and so I'm.
It matches the observation. I mean, obviously the motivation for this is to match the rotation curve of galaxies observation without needing dark matter. It sounds like this paper has some sort of justification built into it based on, I think that's sort of the whole point of this is.
Polarization is a justification for chaos.
So wouldn't that mean that it would be more like what we do Q1 times Q2 in when we're doing QLO force? So then we would just be allowing for, it wouldn't be in
Yeah, I guess.
M1 and M2 could be added positive or negative.
Right, exactly. I'm guessing that's what that means, but I really don't know.
I feel like you're saying that the math matches up, so we're just gonna agree with this. That's just quantum. Just it worked every time we did it, so this is fine.
Okay, that was a fun discussion on the side.
Wait, we need an ACOT.
Oh yeah.
Thank you. We're never actually going to get to any actual class material. That's probably fine, right?
We're talking about
That's good. So here it is. Oh, you're not seeing it. What happened to
It's not the thing we're supposed to be talking
I
about.
have it backwards. Never mind.
Why did my screen not showing anything anymore? There we go. Here it is. APOD. It's a beautiful galaxy.
That's pretty good.
It is. This is M81, I think.
Yep.
M81. Big and beautiful.
You go on.
You,
And maybe one slays.
work it. Okay. Anyway. Here we are. All right, we don't even get to that today, but that's okay. Right, so recall where we were. We had done a derivation that got to this equation. Three GM squared over 5R, and this was the gravitational potential energy of a star, of a spherical object. And we have this single squiggle here to denote that this is a severe approximation because we made a very much simplification assumption along the way, which is that our object was perfectly uniform in density, which is clearly not the case for the sun. And remember what this really is. This is the amount of energy that it would take to pull every single particle off of this star and move it to infinity. Gravitation. That's what it is. Or it's the energy that you get from moving all those particles from infinity to zero. Or to their present location in the sun. So here's a question. This is, we know, not the case for the sun. It's not a uniform density thing. The actual density, of course, of the sun is much bigger in the center than it is on the outside. Does that make this actual sun has rho center much bigger than rho edge? Does this make the absolute value of this estimate more or less than the true value? Or how do I want to say this? Is the actual value of this more or less than this?
Wouldn't that depend on the curve?
Sorry?
Wouldn't that depend on the curve, like whether it's like 1 versus 1
This is big R. This is the total outside radius of the star.
Sure.
So what are you talking about being R dependent?
The density.
It doesn't matter. If it's more dense at the center than the outside, or more dense on the outside than the center, that's going to give you some, right? Imagine the potential energy of a system, right? If all the mass is on the outside, that's going to be a larger potential energy system than if all the mass is on the inside. See what I mean? So, I mean, I just answered the question, but a system where most of the mass is at the center, where the density is much higher in the center, the absolute value of this is going to be smaller because most of it is already concentrated in the center already.
Oh, sure.
Just to try to get some, you can write down these equations, but what do they really mean? It's helpful to think about how these things are related. And again, we define this such that if UG were 0, R would be infinity, right? As this thing goes to an infinite size, the potential energy goes to 0. And it gets smaller as you move it in, but that's getting more negative.
So the true value would be smaller than an approximation. The absolute value would be
Right.
smaller than an
Right.
approximation.
Right. Okay. We need an aside now. So I'm going to spend the rest of the class, maybe, depending on how much time I have left, talking about one of the most important theorems in all of astrophysics, and that is the virial theorem. And if you want a textbook discussion of this, you have to go to chapter 24, which is way in the future. We're in chapter 10 now, currently. But it's important to this discussion, and we'll see why in a second. Have you heard of the virial theorem? A couple of you. Okay. An extragalactic, you did it. Because it's really important. It comes in everywhere in astrophysics. It's just one of those theorems that's really important. And stat thermo?
Yeah, I should have got a homework question.
Excellent. Good job, Dr. Ira. I'm proud of her. Okay, so this is going to be a relationship between kinetic and potential energy in a gravitational bound system. That's what the virial theorem does. We want to derive a relationship between thermal energy, kinetic energy, and potential energy in a gravitationally bound system. Okay, so for spherical symmetry, we're going to derive this thing. Buckle up. And hydrostatic equilibrium. We have the hydrostatic equilibrium equation, which we've already derived. dP dr equals negative rho times g times m of r over r squared. This is the equation of hydrostatic equilibrium that we already derived. M of r, recall, this is a pressure as a function of, going to give us a relationship of pressure as a function of radius in the spherically symmetric object, given the density and the mass interior to that particular radius. Okay, we're going to just do some random stuff now. We're going to bring one of these r's over here. I've got r dP dr equals negative rho gm of r over r. I'm now going to integrate and multiply by 4 pi r squared dr on both sides, because I can. I'm going to integrate from the center of this star to the edge of this star of r times dP dr times 4 pi r squared dr. And that's going to equal negative of the integral from 0 to r of rho times gm of r over r of 4 pi r squared dr. Yeah, we got some volume things going on, don't we? Right, so right, what is this 4 pi r squared dr?
Surface area of each.
Right, so it's a surface area of the shell times dr. What is that going to give you? Yeah, it's kind of be a devolume term, right? Cool. We're going to get to a PDV here thing, which is going to be where we're going with this, right? Okay, what is this whole thing? Density times GMR 4 pi r dr. Think about that. And let's talk about just the left-hand side of this equation and do some cool fun stuff with it.
So, force, right?
So
What?
you're relating like the sum of the pressures to the sum of the gravitational force.
Yeah, that's right.
There's
Yeah.
a pressure force on the right.
Yeah, because they have to the pressure
That's right.
coming out.
That's right. We've got some thermodynamic stuff going on over here, which is going to be fun, and we've got definitely some gravitational stuff over here, which is what we want to bring from thermal stuff to gravitational stuff. That's sort of the point of this. Okay, we're going to integrate this thing by parts. Congrats, Clint. You got the vaccine today. He's pretty excited. So integrate by parts. I never remember how to do this, but so when I say recall, I certainly don't recall it. I'm having to look at my notes now how this works. Integration by parts is integral from A to B of u dv is equal to uv evaluated from A to B minus integral from A to B of B du. That's integration by parts. So what are we going to say? Let's call U 4 pi r cubed, because we actually have an r cubed over here, because there's an r squared and an r. Let's say U is 4 pi r cubed. So we know that du then is 3 times 4 pi r squared dr. With me so far? Okay. Let's set dv equal to, if you can even see this over here, probably not, maybe now. The rest of this stuff over there, dp over dr times dr. And the dr's just go away. Never really understood how derivatives and multiplication and dividing, you can just cross off derivative terms like that. Math mystifies me, but they tell me I can do that, so I just do it. So v then is just integral of dv, which is the integral of dp, which is p. Okay, cool. So we can plug that back in. We get the integral from 0 to r of r dp. This is where we started off on the left-hand side, 4 pi r squared dr. That is u times v, 4 pi r squared p of r, evaluated from 0 to r. Yep. It's not going to matter, but you'll see why in a second. Okay. Minus 3 integral from 0 to r of p of r times, so this is going to be v times du, it's going to be this times this. So the 3 comes out, and we've got 3 pr 4 pi r. This is r squared dr. I see some nods. Okay, I'm on the right track. Good. So let's think about this term. What is the value of this term at r equals 0? 0. What is the value of that term at r equals capital R? Yeah, the pressure basically goes to 0 at the surface. So this is also 0. So this whole term goes away, which is kind of nice. So this thing, 4 pi r squared p of r, evaluated from 0 to r, is 0 both at r equals 0 and r equals dr. And what's the integral of 4 pi squared? What is 4 pi? Oh, and this thing is just dv. We already decided that. Yeah.
Is that 4 pi r cubed or squared?
It's cubed, you're right. But it doesn't matter. Through a squared or cubed, it's 0 either way. You're right. We don't want their mistakes to be on the board, even if it doesn't matter. You're right. Thank you. So this thing is dv. 4 pi r squared dr is just dv. This becomes left-hand side equals -3, 0 to capital R of p dv. And we figured out what this thing is. That, in fact, if you go back and look at our derivation for UG, we sort of started there in our UG derivation. So let's put it back together. Probably go over here, though, so I have some more room for it. -3 times the integral of p dv is equal to UG. Or if we want to move the negative sign over there, 3 times the integral of PdV equals negative UG. So, an ideal gas, we know that P equals NKT. We know that from the Maxwell-Boltzmann distribution, which remember is for a gas of a given temperature, how fast on average, or what the different distribution of velocities in that soup will be. The RMS speed, velocity of a particle in that gas is square root of 3 kT over m. That is the RMS velocity of an ideal gas in thermal equilibrium. So the average kinetic energy per particle of a gas of temp T is 1/2 mvr. Oh, Steve Robertson's calling me. Calls back, I'll answer. And mv squared, right? So this VRMS becomes our V. We can square that. This is just 1/2 times m times 3 kT over m. The m's go away. This is what temperature is, remember? It's an equal partition of the kinetic energies of a gas. So all of them will have about the same kinetic energy, even though they all have different velocities. So this is another thing you've probably seen before, 3/2 kT. So this is per particle. The average kinetic energy per unit volume is 3/2 nkt, right? The n being the volume, this is per particle. If you want the volume density, then you just need the number of particles per unit volume, and that's our little n here. And that is from this guy, where is our 3/2 nkt is just 3/2 p. Yeah.
Where would the volume have been in that ideal equilibrium?
It's in this n, right?
Oh, okay.
This is capital N over capital V, if you want to do it that way. Or just little n, remember, is number density. Big N would be total number of particles in your gas. So little n is big N over V, the total number of particles in your gas divided by the total volume of your gas.
Okay.
Yeah. But astronomers like this better because we're never really talking about the whole star at the same time. We're talking about, the number density in a particular region of that star. And so it's much easier to talk about densities than it is to talk about total numbers of particles and total volumes of gases. I'm going to do it in 10 minutes. If we can get to the variable thing there, that'd be fun. Okay, so we've gotten to 3/2 p. That's a fun one. So where am I going with this? This is where we were. Let's consider this term right here. 3 times the integral of 0 to r of p dv is 2 times the integral of 3/2 p dv. And integrating that thing over the whole volume, this is the average kinetic energy per unit volume. If you integrate over the whole volume, you've got the average kinetic energy of the whole gas. So now we've got the total kinetic energy of the gas on one side, and we've got the total potential energy of the gas on the other side. And we've got a relationship between the kinetic energy and the potential energy of that system. Assuming really, we didn't even have to assume anything about the density being constant this time. This just fell right out. We've only assumed ideal gas law, and that's it. And spherically symmetric distribution in hydrostatic equilibrium. Those are our only assumptions we've done to get to this point. So plug this back in. This is all particles in the gas. We get 2K equals negative U, which is the virial theorem. Sometimes it's written K equals negative 1/2 U, and that's the virial theorem. For a gravitationally bound system in equilibrium, the magnitude of the total kinetic energy of the particles in that distribution is half of the total kinetic energy or total potential energy of those same particles. Once things have settled down and you have some sort of equilibrium system going on. This works amazingly well. It works for stars. It works for clusters of stars. It works for galaxies. Right? If you have a cluster of stars that's sitting there, and you add up the kinetic energy of all the stars moving through that cluster, and add up their potential energy of all of the stars in that cluster, this is, if that cluster has been sitting there a while and isn't being tweaked in some weird way, this will hold. This is a universal truth, and is really useful in a huge range of astrophysical scenarios. So what are the implications? E is the total energy, which is kinetic energy plus potential energy. And that is just, well, kinetic energy is negative 1/2 U. Negative 1/2 U plus U is just 1/2 U. And U is negative, right? The kinetic energy has to be positive. U has to be negative, right, for this to work. U is always negative, the way we've defined it, right? So therefore, the total energy of a star or a cluster is also zero, or also negative, which is odd. But it's the way we've defined this energy that works out that way. What would be the case? What would be like if an object had positive energy? What would happen?
Wouldn't it just be like leaving the gravity, basically the gravity isn't pulling it in and keeping it rotating?
That's right. A cluster of objects that has positive total energy will not be gravitationally bound. It will be leaving. It will be, those particles will be departing. They're moving way faster than their potential energy is holding them together. Therefore, it's not really a bound system. They're leaving. All gravitationally bound systems. Hey, Bill, you can come in if you want to. All gravitationally bound systems have negative energy, but you don't have to if you don't want to. It's up to you.
I'm sorry I'm so late.
That's okay. We got 5 minutes left.
I'll tell you about mine.
Okay. Cool. Okay. So why have we gone through this whole aside on this important but seemingly perhaps unrelated topic at the moment? Let's remember what we were trying to figure out. Can we power the sun by gravitational contraction? That was where we started this whole conversation. So we calculated what the gravitational potential energy, at least a rough approximation for what that would be of the sun. Why have we gone through this aside? As a star contracts, we want to power our star by gravitational contraction, right? As a star contracts, its potential energy changes. Its kinetic energy must also therefore change. And so we don't get out all of the energy that is released when we turn gravitational potential energy into something else. We don't get all of that out for free. Some of that has to go into the kinetic energy of that thing. In fact, this works for deltas too. If you change the delta U by a little bit, you have to change the delta K by something similar, related by a half, right? That's important. So as a star contracts, U goes up, I should say, yeah, absolute value of U goes up, and the kinetic energy must also go up. Yeah, that's right. And exactly, not a little bit, but not almost, but exactly half of the available potential energy must be converted into kinetic energy. Which in this case, in the case of a sun, is heating up the core. What happens to the other half?
It used to expand it back.
It could be, but it's typically not. When the sun was actually in this phase of the sun before it reached the main sequence was generating its energy by doing this thing. And that was how the center of the sun gets hot enough eventually that fusion can start. What is happening to the rest of that energy? It's being radiated away. In fact, this if we want to power the sun this way, we have to be generating light somehow. And so exactly half of the potential energy that we release goes into heating the star, and the other half can be radiated away into space. Okay. I think we can do this in 1 minute. So let's do it. Let's go back to the gravitational time scale, right? Our question was, can we power the sun solely by gravitational potential energy? Well, UG, we know, is -3/5 GM squared over R. The total energy being the total amount of energy we can get out, because it's only half of the potential energy, because half of it's going to go into heating it, is half of that, which is negative. Again, this whole derivation was to get us to a factor of 2, which is probably not even necessary because we're probably more uncertain by the factor of 2 than what we did before. But this is an important derivation to see. It's kind of cool, and it's a really important theorem to get to. So I think it was worth the time. So -3/10 GM squared over R. This is how much energy, if the sun started out at R equals infinity and was reduced down to its present size, we can get out by radiation. This is how much light radiation we'll get out by doing that. And if we plug in, so you can plug in the sun's current mass and the sun's current radius, and you get a number which is about 10 to the 41 joules, which is a lot of energy. Like that's a serious long amount of energy. And there's a thing called the Kelvin-Helmholtz time scale, which I'm not going to talk about right this second. But this is, again, take the total amount of gravitational potential energy you have available to you and divide it by how fast you're using it up, the luminosity. And that's going to give you a length of time that this process can power your star. And we get 10 to the 41 joules, roughly, divided by 10 to the 26 watts or so, within an order of magnitude. And this gives us about 10 to the 15 seconds, which is pretty good, except that's only about 10 to the 7 years, which is only about 10 million years. So you can power the sun for 10 million years just based on gravitational contraction
And that's starting with an initial radius
of infinity. That's
Okay,
right.
yeah, so that's like the maximum. you can have.
This is the maximum you can possibly have. And the assumption that this is overestimating the true potential energy of the sun right now, because most of it's denser at the center. So the true number is even worse than this if you put in a more realistic number for what the gravitational potential energy of the sun is right now. So that's 2 classes worth of lecture to tell you that this is not what powers the sun. Okay, I'll stop there. Have a good weekend, and we'll talk about what does power the sun on Monday.
This is the first time I've ever intentionally missed a class, so I'm really sorry about
Okay, no
that.
problem.
It wasn't the plan.
Have a good day.
Let me just end the